Hello everybody, and welcome to exercise 7 on page 76 of the workbook. Let's take a minute to read this together. So suppose that G is a non-abelian group of order p cubed where p is prime, and that the center of G is not equal to the identity element. Okay, we'd like to prove that the order of the center is equal to p. Okay, let's remind ourselves again what the center of a group is again. Z of G just represents the set of all elements in G that commute with everything in the group. We know that that center is always a subgroup of whatever group we're talking about. Okay, so our strategy here is going to be to appeal back to theorem 9.3 in the section. We'll kind of see how that works as we get deeper into the proof here. We're also going to make use of Lagrange's theorem, which gives us some nice information about what possible subgroups we might have here. So let's start with Lagrange's theorem. Okay, and make the observation that since we know that the center, Z of G, is a subgroup of G, the order of the center has to be a divisor of the order of the group. Okay, so what possibilities does that allow for? Okay, well, it comes down to asking yourself, what are the factors of p cubed? Okay, what are the divisors of p cubed? Well, since that's a prime, the only divisors are 1, p squared, and p cubed. Okay, these are the only factors. Okay, since p is prime. Okay, so notice what we're trying to prove here. We want to prove that the order of the center is p, so the proof is going to kind of proceed in cases. We want to show that the order is p, so we need to rule out the other three possibilities one by one. All right, let's see if we can do that. Okay, so the first one that I claim we can rule out is the p cubed case. Okay, so note that the order of the center can't be p cubed. Okay, why can't it be p cubed? Well, if the order of the center were p cubed, it would match the order of the entire group, p cubed. So it would be like saying that the center contains every single element in the group. Okay, well, what would that mean if the center of G were the entire group? Well, the center is all of the elements that commute with everything in the group. So if the group is equal to the center of the group, it means that all of the elements in G commute with all of the other elements in G. That's just another way of saying that G is an abelian group. And in our hypothesis, we assume that G is non-abelian. That would be a contradiction if that were the case. Okay, so let's see if we can finish this thought here. And hence that G is abelian. But we know that that can't happen. That's contrary to hypothesis. Okay, good. So we have ruled out p cubed. We're down to three possibilities, 1p or p squared for the order of Z of G. Okay, next, note that the order of Z of G can't be 1. Okay, because what would happen if the order of the center were 1? Okay, well, since the center of G is a subgroup, that would mean that it could only contain the identity element, and our hypothesis said that the center is not equal to just the identity. That would also contradict hypothesis. Okay, so let's complete this thought. Okay, this would mean that the center of G is equal to just the identity element, again contrary to hypothesis. Okay, so far what we've ruled out are p cubed and 1. It's down to 2. Okay, so we just need to rule out p squared and we'll have ourselves a proof here. Okay, so to finish, okay, we need to rule out the case that z of g is equal to, the order of z of g is equal to p squared. In other words, we need to show that that can't happen. So let's suppose by way of contradiction that it does happen. Okay, and again, remember, BWOC, that stands for by way of contradiction. Okay, well, let's see where that leads us. If that were the case, then that would mean that if we looked at the order of the factor group, G mod Z of G, that's going to have to equal the number of things in the group over the number of things in the subgroup. Okay, that's the way that we count cosets. Okay, but how many things are in G and how many things are in Z of G? Well, we're going to get p cubed over p squared by our assumption. That's going to give us p. Okay, and p is prime. Okay, but what does that mean? Well, we have another theorem. Okay, thinking way back to work that we did when we were talking about Lagrange's theorem that says that every group of prime order is cyclic. So what we've demonstrated then is that this factor group, G mod Z of G, has to be cyclic because its order is a prime. All right? So G mod Z of G because it has prime order. Okay, but if you look back at theorem 9.3, it tells us that anytime this factor group, G mod Z of G, is cyclic, it means that the overall group G is abelian. And if you look back at the assumptions that we made, one of them was that G is a non-abelian group. So there's our contradiction. We have a statement that's contrary, or an implication here that's contrary to one of the assumptions that we made. All right, so looking back at our list, we have just ruled out the possibility that Z of G equals P squared. That led to the contradiction, led us to the conclusion that G is abelian, which we know it can't be. Only possibility that's left is that the order of Z of G has to be P. Okay, and we're done.